Let's imagine a particle, and one that's going to take up space and repel anything that's like itself. Like, for example, this balloon. Now, this balloon takes up space. If we put another balloon close to it, it's going to push back just from the air pressure. Where we put this one balloon, though, it doesn't really matter. It's not going to change anything. We can rotate it around. But it's just taking up kind of its spherical amount of space. So what happens if we have two balloons? Well, now those two balloons are going to push back from each other, and we're going to find that they tend to oppose each other. They're going to, if we try to squeeze them closer together, they're just going to push back. So even if we have them kind of floating free in space, they're going to stay more or less on their own side, because as we push them together, they push each other back, and they average out to 180 degrees. Okay, now we have three balloons, all starting at the same point, and they're going to push each other to be 120 degrees apart from each other, because that's where they're not trying to get into each other's space. The other interesting thing that you'll notice is that they form a plane, that they all stay pretty much neat and tidy and flat to each other, because if we try to take them out of a plane, then they still have to be closer together, and the air pressure in this case is still going to push them back into that plane. With the fourth balloon, they have to be pushed out of that plane. Let's put the one we're imagining it's sticking right on top of these other three, and now they have to point slightly downwards to make room for that fourth balloon. What we end up with is what we call a tetrahedral shape, where every balloon is pointed 109.5 degrees away from every other balloon, all of them equally far apart. With five balloons, we no longer have symmetry in all directions. There's a real direction in which we can see that there are two that are opposed to each other, and the other three that work around it, kind of on an axis. So these are our three originally, again, that now have to sit still back along what you might call an equator, or in an equatorial position, and then we have two more taking up a position on the axis. So how do the angles on these work out? Well, these ones along the equator, they're back to being 120 degrees apart. But the difference between any one of the axial ones and its nearest neighbor on the equator is 90 degrees. And adding in a sixth balloon, everything's back to equal again. Now we have four along the equator and two on the axis, but which are the equator and which are the axis? So everything is 90 degrees apart, and kind of like the sides of a cube. You can imagine it, each one is going to be the top and bottom, and now we have the four sides all pointed at each other. Okay, that's enough for balloons. So why are we talking about balloons and how they fill out a space around some common central point? Electrons aren't shaped like balloons. Electron orbitals aren't shaped like balloons. We know that they have specific shapes according to quantum mechanics. However, regions of concentrated electronic density are going to behave like balloons, or like anything that's going to repel things like itself. The strong negative charge is going to want to move as far away from each other as they possibly can. And even though these are just balloons and it's a pretty simple model, they're also moving as far away from themselves as they can. Now, this is a classical description that doesn't depend on quantum mechanics in any way, and it's called valence shell electron pair repulsion theory. It's a simple and useful way for us to start translating our 2D Lewis structures into 3D molecular or electronic geometries. In this theory, we count two different types of geometries. Electronic geometries that count all of the regions of electron density, including lone pairs, where we couldn't touch, and molecular geometries, in which we only include bonding electrons, so those that are attached to some atom at both ends. If we have two regions of electronic density, that's called a linear geometry, because the electronic density regions are going to move 180 degrees apart from each other, centered on the atom. Three regions create a trigonal planar electronic geometry. Trigonal because it has three sides, and planar because they all align in a plane, giving themselves as much room as they possibly can. If one of the three sides is a lone pair and the other two are atoms, this is what we call a bent molecular geometry, because that's what it looks like when only two of the things are represented by atoms. The electronic geometry for an atom with four regions of electron density surrounding it is called tetrahedral. If one of those regions is a lone pair and doesn't terminate in an atom, then we call it trigonal pyramidal, because it looks like a pyramid with a triangular bottom. If two of the regions are lone pairs and the other two terminate as atoms, then again we're left with a bent configuration. The most famous or recognizable version of this would be water, where the oxygen atom has two lone pairs and two hydrogen atoms attached. If all of the electronic regions on a tetrahedral geometry are equal, then those distances will be 109.5 degrees apart. But on water, we see that the hydrogens are only 104.5 degrees, give or take. So why would that be? Why would the hydrogens be pushed closer together than if everything was equal? Well, bonded electrons are caught between the two positive regions on the atomic nuclei, unlike lone pairs, which will compress closer to the central atom and stretch out more since there's no second atom confining its direction. This is especially important to remember when we have 5 regions of electronic density. The electronic geometry is called trigonal bipyramidal, but as soon as we start to remove some terminal atoms and replace those with lone pairs, now we have to decide whether those lone pairs are going to be placed on the axial positions or on the equatorial positions. Remember that the equatorial positions have spaces that are 120 degrees separated from their other neighbors along the equator, whereas the axial position is only separated by 90 degrees from any of its nearest neighbors. So the lone pairs will preferentially find themselves on those equatorial positions because they have a greater amount of space to stretch out in. So as we work our way down the molecular geometries, depending on how many lone pairs there are, first we have a seesaw geometry because we can see the two sides of the seesaw are the axial positions and the two remaining equatorial positions act as kind of the legs. Then we would have a T-shaped for the two axial positions, and one of the equatorial positions are still leading to terminal atoms. And the third set of lone pair electrons will also take an equatorial position, leaving us with the terminal atoms in the axial positions and a linear molecular geometry. An octahedral electronic geometry starts with equal angles all around, 90 degrees between any two terminal atoms with the axis at the central atom. And similarly, as we start replacing those terminal atoms with lone pairs, we work through square pyramidal, square planar, since the two lone pairs will oppose each other and leave the bonded atoms along the equator, forming a square. Then T-shaped, and finally a linear geometry, again because the lone pairs are going to take up as much space as they can, leaving the bonded atoms 180 degrees opposed to each other. Vsepr does a decent job in predicting the molecular geometries of actual molecules based on nothing but the 2D Lewis structure. However, calling it a theory might be a little bit generous, because we still have no idea how we go from these quantum mechanically derived atomic orbitals into these different shapes, different electronic geometries, which define molecular bonding. A classical theory like this one can't explain electronic orbitals because orbitals don't exist inside of classical theory. That's a purely quantum mechanical effect, and we need a quantum theory solution for that problem. Later this week, we're going to discuss methods to combine the classical molecular geometries with quantum mechanical orbitals. No more balloons, though.